Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. I just love that quote. Those are the immortal words of visionary physicist Richard Feynman, way back in 1981. It was this incredibly bold declaration that basically challenged everything we thought we knew about the limits of technology. And honestly, today we're watching that exact vision become reality right before our eyes.
Welcome to this explainer. Okay, let's dive into this, because we are about to explore a paradigm shift that is so massive. It's not just going to change our computers. It's actually going to ripple out and completely reshape global security, international power dynamics, and surprisingly, even the fundamental ways we tell stories as human beings. It's a wild ride.
So, here's a quick look at our roadmap for today. We're going to cover the physics breakthrough, escaping current computing limits, the cryptography ticking clock, the geopolitical race, and finally, designing quantum narratives. It's a highly structured journey taking us all the way from microscopic physics to global human culture.
First up, Section 1, the quantum physics breakthrough. To really grasp the macro impacts later on, we've got to first understand the subatomic rules governing this whole new frontier. Now, what's really interesting about this slide is how it highlights the exponential leap we're taking. For decades, our entire digital world, your phone, your laptop, even global supercomputers, has run on classical bits. They're just tiny switches stuck in a strict binary state, purely 0 or 1. But quantum computing, it uses what we call qubits. Because of the totally bizarre laws of quantum mechanics, a qubit can be a 0, a 1, or, and here's the crazy part, remarkable combinations of both states simultaneously. It essentially replaces the rigid limits of either-or with the infinite massive potential of both and. And this mind-bending reality happens through two absolutely crucial phenomena. The first is superposition. This is what allows these microscopic systems to explore numerous pathways and possibilities all at once, rather than just grinding through them one by one. The second is entanglement. This is where particles become mysteriously connected, instantly influencing each other across vast distances. I mean, it's a concept so wild that Albert Einstein famously dismissed it as spooky action at a distance. But you know what? That spooky phenomenon is very real, and we are literally harnessing it today.
In fact, just recently, a team including researchers Michael Knapp and Pedram Roshan did something incredible. They used Google's quantum processor to actually simulate the hidden fundamental rules of the universe. They looked at gauge theories and literally observed how particles and the invisible strings connecting them evolve, fluctuate, and even break over time. By observing these high-energy particle physics analogs right there in a lab, they definitively proved Feynman's 1981 theory totally correct. You really can use a quantum system to simulate fundamental nature. Mind blown, right?
Which brings us to Section 2, escaping classical compute limits. Removing from theoretical physics into hard technological realities, because our current supercomputers are hitting a serious, inevitable wall.
You've probably noticed the tech industry is completely buzzing right now about the compute singularity. Futurists like Ray Kurzweil and tech leaders like OpenAI's Sam Altman are making some intensely aggressive predictions that we're basically crossing an event horizon. We are rapidly approaching a point where machines start improving themselves faster than human intuition can even track. And doing that requires vast, exponential leaps in raw computational power that our old, classical hardware simply cannot sustain forever.
So, the crucial point is this number right here, 5 minutes. Google recently announced that its brand new Willow quantum chip solved a complex computational problem in just 5 minutes. Now, to put that into perspective for a second, if you gave that exact same problem to the fastest, most insanely powerful classical supercomputer on Earth, it would take longer than the universe has existed to find the answer. 5 minutes versus the age of the universe, that, my friends, is the true scale of the quantum leap.
And this monumental leap unlocks what is being called the quantum AI flywheel. It's essentially this massive recursive feedback loop. Right now, artificial intelligence is being used to discover novel, highly stable materials to build better quantum components. Well, those better components then go on to create vastly more powerful quantum computers, which, you guessed it, are in turn used to train even smarter, more capable AI. They are perpetually accelerating one another straight toward that compute singularity we just talked about. It's like a technological snowball rolling down a mountain.
All right, let's turn to Section 3, the cryptography ticking clock. We need to raise the stakes here and look at global digital security, because there are some severe vulnerabilities hiding in our current encryption. Security experts have a name for this looming threat. They call it Y2Q, or Q-Day. It's obviously an homage to the whole Y2K bug, but honestly, the stakes here are arguably much, much higher. Y2Q is this hypothetical future date when a quantum computer finally becomes powerful enough to just completely shatter the strong encryption algorithms that protect the world's data today. We're talking diplomatic cables, critical infrastructure logs, global financial networks, intellectual property, and yeah, even your personal banking data and private messages. Essentially, everything protected by current public key cryptography becomes instantly readable overnight. It is quite literally a ticking clock.
Now, you might be sitting there thinking, well, hey, Q-Day hasn't happened yet, so my data is totally safe today, right? But that totally ignores a terrifying, very real surveillance strategy known as Harvest Now, Decrypt Later, or HNDL. Right this second, adversaries are intercepting massive amounts of heavily encrypted communications. They can't read it today, obviously, so they're just quietly storing it in these massive, sprawling data centers. Step by step, they are simply waiting for Y2Q, when they will finally have that quantum master key to just unlock decades of deeply sensitive, heavily guarded global secrets.
But thankfully, to defend against this, there is a massive global transition currently underway. Software systems are being urgently upgraded to post-quantum cryptography. These are algorithms that are actually thought to be secure against a quantum attack. But since that data can still be harvested in its encrypted form, we're also seeing this major shift toward physical layer security. Companies like Cybersecurity, for instance, are utilizing optical layer encryption. This is basically photonic shielding that buries fiber optic signals deep in optical noise. Think about it. If an attacker can't even record a valid signal in the first place, you completely eliminate that initial harvest phase of the threat. It's brilliant.
Moving right along to Section 4, the geopolitical quantum race. As you can imagine, the fear of Y2Q and the promise of the singularity have sparked a wildly high-stakes global competition.
When we take an objective, completely impartial look at how the world's two largest economies are approaching this, we see two fundamentally different resource allocation models at play here. The United States is heavily leveraging a public-private partnership model. Basically, the US government is actually taking direct equity stakes in private startups, using public funds to sort of de-risk those investments and supercharge the decentralized, fast-paced innovation of Silicon Valley. China, conversely, is utilizing a state-controlled, highly centralized approach. They are pouring tens of billions of dollars into these massive top-down national laboratories, which allows for some incredibly coordinated long-term state planning.
But here's the thing. Regardless of which model they use, their geopolitical strategic priorities are strikingly similar. We're seeing a rapid, intense rise in supply chain nationalism. Governments are desperately trying to domesticate the sourcing of all these critical components, things like highly specialized, high-powered lasers and extreme cryogenic cooling systems. We're also seeing heavy investments being channeled directly into defense-first applications, like quantum sensing and networking. And that's exactly why the US is taking those unprecedented equity stakes in domestic tech firms like IonQ and Rigetti. Make no mistake, this is a full-scale global mobilization to secure technological supremacy. Finally, Section 5, Designing Quantum Narratives. Let's move to and see how this builds on what we've discussed, transitioning away from hardware and geopolitics to see the truly surprising impact quantum mechanics is having on human culture itself. Think about it. For over 2,000 years, human storytelling has strictly followed these rigid, Aristotelian rules. You know, a linear plot where characters serve the narrative and audiences just sit back and act as passive spectators on a fixed railway. But as experienced designer Stephanie Riggs astutely points out, this rigid structure completely collapses the second you enter modern, interactive, immersive worlds like VR or AI-driven sandboxes. When the audience can actually move and touch and choose things, linear plots just break. So we're shifting toward what she calls quantum narratives. These are fluid, highly dynamic systems that actually behave way more like complex weather patterns, generating emergent, entirely new meaning based on the active, unpredictable choices of the guests. And this brilliantly illustrates the brand new toolkit creators need to build these responsive worlds. Riggs outlines 5 new foundations. Instead of just scripting a fixed plot, designers now have to build influences, which is like the thematic gravity of the world. Then they design sensory forms, the actual objects, signals, and cues the guest perceives. They establish dramatic flow through underlying system rules and behaviors, and dynamics through intersecting competing factions. And finally, you have the absolute most important variable of all, the guests themselves. They are no longer treated as passive observers, but as highly active, totally unpredictable agents whose very presence alters the final outcome. In a quantum narrative, the story doesn't just happen to them, it happens with them.
So, bringing it all together, from literally simulating the invisible threads of subatomic particles, all the way to architecting these vast, responsive narrative worlds where human agency actually matters, the quantum revolution is fundamentally about moving way beyond the old limits of classical thinking. It's really about embracing an entire universe of interconnected, simultaneous possibilities. Which leaves us with one final, deeply provocative thought as we close out this explainer. If our new machines can actually simulate the hidden strings of the universe, are we finally ready to rewrite our own place in it? Thank you so much for joining me on this deep dive into the quantum frontier. Stay curious out there, and I'll see you in the next explainer.